Thank you very much, Enrico. I cannot see you the way I've set it up, so please interrupt me at any point to ask me questions. So I want to talk about some recent work that I've been doing with Kostis Papageorgakis at Queen Mary, Alex Stratoudakis, who is a student of mine in Crete, and Mitchell Gouli, who is a PhD student at Queen Mary. So although I'm going to talk, most of the talk is going, and the main applications are going to be focused on the thermal bootstrap, which is the subject of the seminar series. I should start by saying that this problem for us is much more general. We've been thinking about it in different ways for a few years now. And our main motivation is basically to find some new way to do the primal bootstrap in general contexts. So I want to start by explaining the general idea, and then I will apply it to the thermal case. So in many CFT bootstrap problems, we need to analyze some rules of the form that I have here. Okay, so this is the kind of equation we want to solve. Written schematically here, there's some quantity which is expressed in terms of some quantum numbers like scaling dimensions and spin. This quantity, usually involves some complicated functions like conformal blocks in terms of the scaling dimensions. But most importantly, it typically contains an infinite number of CFT data. So it's an infinite series. So prototypical example maybe is the example of the 4-point bootstrap. When you write down the crossing equation, then you have this for 4 equal operators, 4-point function of 4 identical operators. C is the OP coefficient squared, and F are crossed blocks. Now, one might be interested in constructing explicit solutions of this equation, but that is hard for 2 reasons. First of all, because it involves an infinite number of CFT data, so it's hard to actually produce a solution for infinite set of data. And the second one is that if you just have this equation and not other constraints, then typically the number of solutions is not 1. It's not a unique solution. So the linear functional method by Ratazzi, Ryzhkov, Tony, and Vicky in 2008 bypassed this problem. It's a very successful workaround. It yields feasibility constraints that can be analyzed with a powerful convex semi-definite programming algorithm like SDPP. And we all know the advantages of this method. It has been very successful. It has produced very nice results. It is rigorous. It produces generic statements about CFTs. And if you can identify some special features like cusps or even better islands, then you can hone in into some theory, and there you can say a lot of things about it. But there are also limitations. For example, it is unclear how to drive the assumptions to a theory of interest. So if I'm interested in solving, I don't know, like QCD in the conformal window, it's unclear how to set up the assumptions before solving the theory to drive myself to that theory. It's difficult to scan high-dimensional parameter spaces. There's no intuition about the bulk of the allowed region. SDPP can sometimes be expensive in multi-correlator bootstrap, although in recent years, technical advances have been made. And it's inextricably tied to positivity. So there are many interesting contexts that are immediately out of reach, like Finite, which is a topic of interest here, defects, higher point bootstrap, non-unitary theories, etc. So for all these reasons, you might be interested in a constructive approach where you actually construct solutions to these crossing equations. Again, they may not be unique, but maybe you want to scan overall possible solutions or subsets of solutions to get a better intuition about the problem. Or the assumptions you would like to feed into the other algorithm, if the other algorithm is applicable. But that will be useful if one can tame the infinite dimensionality that I mentioned previously without losing control of the systematic error. So in previous approaches, the way one would proceed in order to construct solutions, to solve explicitly the equations and not just ask about feasibility conditions was, first of all, to do hard truncation. So you have this infinite sum, you truncate it somewhere, you expect or assume that the the rate of convergence is fast enough. So by keeping a sufficient number of terms, you're approximating well your problem. And in this problem, in this approach, which is so-called Gliozzi approach from 2013, you drop the high energy tail contributions. And this is typically uncontrolled because in many cases you don't know where to put the cutoff, etc. But there has been some interesting advances or some interesting applications in this context. For example, a very nice paper by Hu and Li very recently in the boundary bootstrap in the 3D Owen vector model. Another more nuanced approach is to do soft truncations. In other words, don't drop the high energy tail contributions, but try to model them in some way. And this is what we did for one defect, for the one defect bootstrap, for the bootstrap of the half BPS Wilson line in N-cos4 Sperring-Mills theory. In this paper with Kostis and collaborators. There, the idea was to model the high energy tails using what we call the soft tail modeled through some effective operators. In the thermal bootstrap problem, Enrico, Eli, and Alessio have also have essentially implemented the same approach using Tauberian theorems, and then they get very nice results. Now, although this is clearly an improvement compared to the blind hard truncations, it is still hard to implement this approach in generic context. Basically, it's very hard to control the systematic error. I should emphasize that in this paper in 2023, when we did this soft truncation approach, where you can see here 3 results for 3 OP squared coefficients on the Wilson line defect, you can see that we could produce rather cheaply the results of the same accuracy as SDPP, and the approach was much cheaper because we didn't need to work with hundreds of digits of precision, but only 16-digit precision. So what I want to do today, and it's one of the main results of this work, is to propose a new way to think about all of these crossing equations, and this can in principle be applied in many different contexts, not only in the thermal bootstrap case. And the idea is to bootstrap everything. Basically, not only bootstrap a few low-lying CFT data, which is usually what we expect from the numerical bootstrap, but also bootstrap also the tails of high energy data. In other words, try to reconstruct an approximation of the full correlation function. And the general idea is the following. So this is the kind of crossing equation that we have. It has a sum typically over spins and scaling dimensions. And the idea is to break it up in different pieces and try to handle the different pieces in different ways. So let's talk first about the contributions that have spins greater than some J star. So I pick some spin cutoff, I call it J star. I call it high spin part here, but J star is chosen arbitrarily. As you will see later on in the applications, it doesn't have to be small. I don't need to guess where to put it. It's just a choice. And then this high spin part, which also involves arbitrarily high scaling dimensions, is going to be modeled or expressed in terms of dispersion relations. And this is the only place where I'm going to do an approximation. So the approximation will go into how I will approximate the dispersive, basically the discontinuity or double discontinuity in other contexts of the correlation function. But I will try to argue in the thermal bootstrap context that the approximation will be controlled in a specific manner, okay, which I will explain. So this is the high spin part. Let's discuss now the low spin part. The low spin part has all the contributions where J is less or equal than J star. You still have to add all the contributions from the infinite set of scaling dimensions. In this part, I will not make any approximations. Okay, I will not drop anything. I will not model anything. Okay, but I will break it up into 2 pieces. At its spin, there is a tower of scaling dimensions. And at each one of these towers, I will pick some delta star, a cutoff in the scaling dimension, which I will call delta star. It depends on J. So it's a delta star of J. And this cutoff, again, is not chosen so that I have converged or whatever. It's just some arbitrary context. For example, I can put the cutoff right on the unitarity bound, for example, and then put basically nothing on this contribution. Okay, put everything on the other part. Then so this part here has J less or equal than J star, delta less or equal than J star, delta star J, and it's a finite number of terms. So it contains a finite number of unknown CFT data. I will call them D because it's a discrete set of data that in principle I don't know and I want to find out. The data that appear in this term, I will also call exposed data because they will be explicitly, they will appear explicitly in my equations. All the rest is again an infinite set of a sum with an infinite number of terms. The spin is low, it's less or equal than J star. And the scaling dimensions now are above this cutoff. So here, this part is the hard part, because in this part I have an infinite sum of terms. So the question is, how do you model, how do you handle this part? Okay, because it involves an infinite number of terms. So the low spin high energy part, which is this one here, can be written in several situations and automatically, in fact, in the thermal bootstrap case, as a sum over spins for spins less or equal than J star of basically each of the terms factorizes into a function of R, some radial function. So maybe I should have said it already. Let me go back a little bit. When we write this crossing equation, typically this comes, say, from a 4-point function or a 2-point function, has some space-time dependence, right? And then in order to solve this equation, we'd either choose some points in the plane to evaluate this function, or we take derivatives at some point. And this is how you select a finite number of sum rules out of this equation that typically depends on continuous parameters. Okay, so now in this equation here, I view again the crossing equation or the crossing vector, if you want, as a function of the space-time coordinates. And in terms of space-time coordinates, it can be written as a function that depends on a radial coordinate and a function that depends on an angular coordinate. Here are Gegenbauer polynomials. So there is a way to write this thing as a sum of factorized terms where you have unknown functions. These unknown functions are a power series that involve an infinite number of scaling dimensions, unknown scaling dimensions. And the rest, which is independent of R, captures the angular dependence of this particular contribution to the correlation function. So the idea now is, instead of focusing on each individual scaling dimension or OPE coefficient that appears in these terms, the idea is to package them in a set of functions, a finite number of functions, because J now has a finite number of values. And the idea is to try to vary or explore solutions in terms of this unknown functional data that I will call F for functions. Okay, is the idea clear? Yes. Where should I go? Yes. Here. Yes, this one. In this AJ, exactly. Right. Exactly.
But and J star, of course.
And J star, yeah. J, you sum over all the J's less or equal. It should be equal here also. J star. The J star is your choice. You put it there. Okay. Yeah. You don't need right. That's an important thing to realize. Usually, when we put a cutoff, even these cutoffs delta stars, right? When we do truncations, we have to pick them carefully, so that assuming that the series has converged. Okay, and they are in some sense real cutoffs. Okay. But now they are not real cutoffs. It's just a choice, an arbitrary choice of how to partition the different contributions in this equation. So if I change delta star or if I change J star, I'm just simply shifting things from one term to the other. So if I make, yes, go ahead. Yeah, in principle, it doesn't influence the final outcome. It will start, some aspects of this are going to start influencing the outcome once, once the approximations are, once I do some approximations. So once I do some approximations here, you will see exactly what happens later on in examples. Then that approximation, like very small J star is not going to be very good because, my approximations here are not going to be great. Okay? But as I increase J star, this approximation, this is the controlled part, these approximations will become better and better.
So this J star is not the same J star that people define when they do inversion formula, right? Because there is not a
right.
choice.
No, exactly. It's not that. It's not that.
Okay, sorry. Okay.
Exactly. No, it's good that you're asking all of these questions. I want to emphasize that it's different. It's not a traditional cutoff. It's just a partitioning of different contributions in the equation.
Maybe a stupid question looking
Yes,
forward.
go ahead.
Is there a physical motivation for which J star to choose?
I will tell you later on. Before any approximation, there is no motivation. After the approximation, I will show you examples, and then I think you will see clearly how I do it. Okay. There is a compromise to strike, basically. A lot of J star, you will see it later on. This answer, I think, will be, this question will be answered clearly later. So I will come back to it later. Okay, so let's see, what's the goal here? There is a finite dimensional vector, here it is, that we want to basically, if you want to measure, we want to set to 0, we want to set that vector to 0. It depends on a finite number of data that I call D, discrete, and the number of functions, unknown functions, but it's a finite number of functions. And I want to minimize basically the size of this vector, okay, in order to satisfy these crossing equations. And in other words, I want to minimize a semi-positive definite functional, which I will call a loss, that depends on discrete data, numbers, and some functions to determine solutions of the crossing equation. Now, the part that has to do with numbers, the discrete set of numbers, is easy, right? You just do some optimization. The optimization in general is going to be non-convex or non-linear. But the other part, the part that has to do with the functions, is more complicated because I have to vary over functions now. I have to solve a variational problem over functions. And that requires a flexible way to vary over the functional data F. So here you could choose your own favorite way of tackling the variation of the functions, expanding in some bases that is well motivated on physical grounds for the problem at hand. Or a more flexible way, I will try to argue, is to model these functions in terms of neural networks. So neural networks are function approximators, and this is how I'm going to use them here. So there's a finite number of one-dimensional functions that depend only on R. I will model them in terms of neural networks, which are expressed in terms of a finite dimensional vector. I will call typically theta, as people do in machine learning. And the number of dimensions for this vector can range from thousands, like in the examples that I will show you, it was of the order of thousands, but it's also very easy, like on your laptop, to have millions of dimensions here. Okay, so let me summarize. We use the idea here is to use a combination of dispersion relations for the high spin part and trainable functions for the low spin, high dimension part to capture unknown correlation functions and the CFT data they contain, and try to fix these functions by imposing suitable constraints. I talked about the crossing symmetric constraint, but you could impose here any other sum rule or constraint that you like. And the more rules the more sum rules or more constraints that you put in, the more constrained the optimization problem is going to be. I want to, like in passing, let me also say that there have been several approaches on the primal bootstrap in the S-matrix bootstrap, and some of them are using ideas that are very similar to this one. Not exactly the same one or all the components together, but many of the words and concepts are related, like this paper in 2022 by Grigeri, or this paper by Sasha Ziboedov and collaborators that actually uses machine learning techniques, neural networks to do the optimization, etc. I won't talk a lot about machine learning here. It's not the most interesting part of the story. But I want you to know what a neural network is, basically what it does for me. And what it does for me is basically parameterize a generic function, okay? And the way it parameterizes it is a bit stupid. It's basically, this is the input X, and you want an output that can be a vector itself. And the way you produce it is basically you act first with, it's basically a composition of functions, and all these W's are linear transformations. So you act on X with an affine transformation in this way here. Then you compose element-wise on this vector a nonlinear function, for example, a function like tan H. Then you do it many times, and each time you say have a different layer. And this is how you produce a function. And there are universal approximation theorems that tell you that if you choose these layers wide enough, then you can approximate any function, some general class of functions. In this problem that we want to solve, we have an output. The output is not going to be a single function in general. Depending on what J star is, you're going to produce for its spin different functions. So we have a set of functions that we want to model. And we find it convenient to use an architecture that is called a multi-branch, multi-layer perceptron model, where initially there is this linear layer that is takes the whole input into that linear layer. The size is 256 in the particular applications we did. And then the network breaks up into different subnetworks. Each subnetwork is dedicated to learning, modeling the function for its spin. That's the idea. Another thing to mention here is what kind of loss I'm going to use. Basically, how am I going to measure the error I'm doing in the crossing equation? So let me call f the crossing vector. I'm trying to set it to 0. And one simple thing that I can do is just take, for example, the components of this vector, take the norm of this vector, the standard norm, L2 norm of the vector, and try to set it to 0, okay? This is not a unique choice. Obviously, I can use an LP norm, something like this one, where P is greater or equal than 1. For example, P equals 1 is where I'm summing the absolute values of the components of this vector. We did this, but we also proposed in the paper another loss that we call a dot loss. And it turned out that this one is much better. And this can be constructed in the following way. So in one version of the problem, let's say that I'm trying to solve this crossing equation here, this equal to 0. And let's say that the crossing vector is expressed in terms, and let's say that I'm not exposing any operators. That means when I do the split here, I'm putting nothing on this part. Okay, so delta star is very low. So I'm not exposing any operator, any CFT datum. Everything is hidden inside the unknown functions. Okay. So in that case, the crossing vector, roughly speaking, has the following form. It has a part where I have something like the identity contribution or, some datum that I know. And this part is, or for example, the discontinuity part that I have modeled in some way. Okay, and this is, let's say, a known function. Okay. And then the rest contains the unknown functions. It depends on the neural network parameters theta that I'm optimizing over. So this is the form of the neural network. So no exposed operators, no exposed CFT data. So the set of discrete data here is empty. Now, one thing I could do is just take the LP norm of this vector and try to set it to 0. So in other words, change all these thetas so until the norm of this vector becomes very small. Another way you can do it is the following. Imagine that you have this vector h, you have this unknown vector g theta, right? With some angle phi, and then you start changing all these neural network parameters. In other words, you start changing your unknown functions so that this vector, what does it have to do? Well, first of all, it has to go parallel to this vector h, and then it must also be, the parallel component must be equal to h. Okay, so these are essentially, I'm splitting the directions of this vector in normal to h and parallel to h. And for the normal, I'm trying to basically set this angle to 0, or if you want, I'm computing the cosine and I'm trying to set it to 1. Okay. Because there's a dot product appearing here, we call this the dot loss. In another version of the problem, maybe, for example, you have in the discrete data, you're exposing one single datum, one low-lying datum, and you say, this is the one that I want to explicitly compute, and all the rest is put into the tail functions. Then the crossing equation will depend on your unknown datum, and here anticipating the thermal bootstrap problem where the unknown thermal OP coefficients appear in front as a constant linearly. F will take the form A, your unknown one-point function, for example, in the thermal bootstrap time across thermal block, which is known, it's a known function, plus everything that has to do with the tails, plus something that is explicitly known, like the identity contribution or something, or something else. Then in this case, you can do again the same thing. You can try to change g theta so that it goes, you can try to change g theta so that g theta minus h, this vector, goes parallel to f. Okay, so for g theta minus h, you try, and this is f instead of h, you try to make the angle small. So you try to make the dot loss, this dot loss small. And once you achieve that, you have achieved g theta to be parallel to f, and then you solve the parallel part of the equation exactly, and you determine A. So in this way of doing things, I'm not optimizing over A, I'm just getting it at the end after after optimizing in terms of the unknown functions. So I will use this later. So is this okay? Should I stop and ask, are there any questions about this? Okay, if there are no questions, then that's the idea. And now let's go to the thermal bootstrap and try to apply it here and see what we get. As you will see, in principle, the idea is nice in terms that, not introducing unknown stuff. Obviously, as you start implementing it, all sorts of difficulties can arise. And part of the project here was to identify where the difficulties with such an approach will arise. So you will see that difficulties arise and we will try to address them. Okay, so let me set up the notation here, although I think most of you are experts, so I shouldn't stay too long on this one. But I just want to set up the notation. We're going to consider two-point functions of scalar primary operators in d-dimensional CFTs on S1, the thermal S1 times the d-1 dimensional plane. Since we break the d-dimensional rotation invariance, now the two-point function of the two scalar primary operators depends independently on the time coordinate and, if you like, the d-dimensional norm of the separation x minus 0. X vector is the spatial part, tau is the time part, and I'm going to use the d-1 dimensional rotation group to set all the space separation coordinates to 0, and except for the first one that I will call sigma. And then I define Z as usual as tau plus I sigma, which I also can express in terms of a radial part and an angular part. Okay, so this is the radial part that I was talking about previously. And Z bar is the complex conjugate version of this. And the KMS condition, the Kubo-Martin-Schwinger condition, tells you that the two-point function is periodic on the S1, which you can rephrase as this condition here, or this condition if you want. G of 1 minus Z bar is the same as G of Z bar in terms of this complex coordinates Z. Now, in this way, it looks very similar to also the 4-point bootstrap on the plane, where you have the cross ratios Z and Z bar. The KMS condition is a non-trivial constraint for the thermal one-point functions in the thermal operator product expansion. So you can express, you can do the thermal operator product expansion in this way, in these variables. These are Gegenbauer polynomials. They depend only on the angular part. And then you have powers of R here. So again, roughly speaking, these functions aj that I was mentioning basically are doing the radial, the sum of over the deltas at specific j of, and it's a power series, a delta times r to the delta sum over delta. So this is basically what they are. And AO is expressed in terms of the 3-point coefficients, coefficients F, phi, phi, O, and the thermal one-point function, one-point functions BO, and CO is the 2-point function of phi, phi. Now, what is the goal of the thermal bootstrap? One would like to use this equation as a non-trivial, the KMS condition, this condition here, as a non-trivial constraint on this thermal OP data, assuming knowledge of the spectrum. Now, that's the ideal goal. Of course, we never know explicitly the whole spectrum in order to implement this program in the way I just phrased it. Except for some very simple cases like the GFF case that I will mention in a moment. But generically, we don't know the whole spectrum, and that is one of the complications, practical complications. I mentioned this because, it will be good when we implement the thermal bootstrap to have an economical way of treating the data, okay? So now let me be very specific about how I do the low-high spin and low-high scaling dimension split of the 2-point function. Here we can see explicitly how it arises and how also the dispersion relation part comes in. So the first line on the right-hand side contains all those data that I call exposed data for with scaling dimensions less than my delta star cutoff, and for j less or equal than j star. Okay, so here you can see I assume in the standard way that I know the deltas, and I want to determine this unknown thermal coefficients, thermal OP coefficients A delta J. And it's a finite number of numbers, CFT data. So this first term is what I call the exposed data. Now, the low spin high delta part, which is expressed in terms of the tails, is this one here. And you can see here how these functions A of R appear. Again, if you look at this expression here, basically I'm doing the sums of the deltas for specific J, and the angular part just comes out, factorizes out. And it's a finite number of tail functions. And then I have all the contributions that have J greater than J star, and then you can use a dispersion relation to express them in terms of the discontinuity of the function in W. So the analytic structure of the 2-point function is such that when we analytically continue on W, there's a branch cut starting at R to the power -1 to plus infinity, and from minus infinity to minus R to the power -1. Using the OP inversion formula, you can write down a space-time dependent dispersion relation where you have subtracted out the contribution to the OP, to the thermal OP of all the operators with J less or equal than J star. So again, let me put it in another way. It is possible, as you know, and you have also written, people here in the audience have written papers about this, it is possible to express the whole G in terms of an integral over the discontinuity in terms of a kernel that is space-time independent. But now I'm doing a subtracted version of this where I'm subtracting the low spin part and I'm trying to write the rest as a modified kernel that depends on J star and also the scaling, the space-time dimension multiplied by the discontinuity. And the J star dependent kernel looks like this. So you can see in particular that as I try to send J star to infinity, basically I'm reshuffling the data on the high spin part back to the low spin part, and the high spin part goes to 0 because kj star goes to 0. Yes. Mm-hmm. 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 So you mean these ones or these ones? So the first ones, yes. No, this contribution, this kernel is such that this data here from the first and the second line are subtracted. They're not there. So it's not a traditional K that you get, for example, also from the Cauchy theorem. It is engineered in such a way, exactly, to capture only the contributions for J greater than J star. And this was written in some form in this paper from 2020 by Aldai, Kologlu, and Zhiboedov, and it also was discussed in the MSc thesis of Alex in 2024, where I think he was, I think it was, as far as I know, the first attempt to try to apply these dispersion relations to see if, you know, we can get some good approximation to two-point functions, etc. Good. So, and then of course, yes.
Sorry, what is fj in the last line?
Sorry, which one?
Capital
fj. Sorry, I should have included that definition, some combination of hypergeometric functions.
Okay, thanks.
I should have included this. I forgot to do that. Yes, thank you. I will do it. Okay.
Maybe just another question.
Yes, go ahead.
Can you always resum the high conformal dimension data into capital A delta? Like in going from
yes.
It's a definition, I agree, but
as long as the OP converges, I can do it, right?
Okay. Even if you have an infinite amount of stuff.
Yeah, because it's part of the OP. I'm just writing the OP. I'm just writing parts of the OP.
Okay, thanks.
Right. Okay, so a few comments. J star, as you were asking me before, J star is arbitrary. High J star suppresses the discontinuity part and puts all the info into the tails. Now, if I do that, right, maybe I don't want to put anything in the discontinuity part, or I put everything on the tails, right? I have an infinite number of tails. It's not practical because I have an infinite number of tails to optimize over. And also, if I want to use the discontinuity, you know, some information in the discontinuity to guide the search, you know, I'm not doing it in this way, right? Like have some generic crossing equation with not a lot of input. Well, the spectrum is input, of course, but other than that, there's no other input. And if the KMS condition has many solutions, you know, I cannot distinguish between them. If I make J star very small, then, you know, I'm putting more and more contributions to this term. And now I have to deal with the fact of how I approximate this term, right? Because I don't know, I haven't solved this problem, so I don't know what G is, so I don't know its discontinuity. So I have to model it in some way. So one way to do that is, I can go to the cross channel here, and I can use again the T-channel OP expansion, say the first few terms, okay, to approximate that discontinuity. There are two problems with this. First of all, I'm making an error because I'm keeping a finite number of terms. And secondly, as you know very well, since I have to integrate here over W outside the region of convergence of the S&T channel, the convergence region of the S&T channel OP expansions, this is not valid. I cannot use everywhere the OP expansion to model the discontinuity. Now, this is a problem, okay? And if I try to if I take J star very, very small, I'm putting more and more contributions here, so the error I'm doing is larger, okay? So practically, I don't want to take J star to be very, very small, okay? I don't want to take it very, very large because I'm not putting anything in the discontinuity, and I have to solve a harder problem with the unknown functions. So the compromise I was trying to allude to before was some medium range J star where I have enough where I can put safely some information in the discontinuity and then some information into a finite number of tails. Now, I'm still making an error, but as I increase J star, this contribution becomes smaller. Not only that, if you plot this function here, you will see that it's highly concentrated around r to the power -1 and minus r to the -1. So this kernel has such a form that it's very concentrated around the beginning of the branch cut. And therefore, it suppresses automatically, at the moment you put that kernel there, it automatically suppresses the errors you're doing from W's that are trying to take you away from the convergence region, okay? So this is why we say that having this KJ star here gives you a systematic way to suppress the error you're typically doing by approximating the discontinuity with an OP expansion. And we will test this later on very, very soon with specific examples. Okay, so this is what I write here. The discontinuity will be approximated using the cross-channel OP. This introduces errors. Part of the W prime integral is outside the common region of convergence of the S&T channel OPs. The cross-channel OP is truncated. Both issues are mitigated by the kernel KJ star, which suppresses the integral away from the branch points, as well as the higher twist contributions. So if the discontinuity is partially known, the corresponding information acts as a source guiding the search towards specific solutions. That is another benefit of having the discontinuity there. Now, before we go to examples, why is the thermal bootstrap easy and why is it hard? It is easy, or so it seems at first sight, because the K-means condition is superficially similar to the 4-point crossing equations at 0 temperature on the plane, and the spectrum is fixed. So for us, who were trying to solve bootstrap problems on the plane, that seemed like a very simple case. Like, you give me the spectrum, okay, great. I don't have to optimize over unknown scaling dimensions. The thermal blocks are simple and fixed. And it looks like a linear regression problem. Like, you only have the unknown coefficients appear linearly, and you have to do a least squares. You have to solve a least squares problem that has a unique solution. Now, it turns out these features that make the thermal bootstrap easy, they make it also very hard, because there's no positivity and the OP convergence is very slow, as you have shown in your previous papers. But more than that, any estimate of the OP tails with a fixed constant, for example, one that arises from a Tiberian theorem or a finite number of variable CFT data, leads to a linear regression problem, and that has a unique solution. But we know, as we will see later on examples in the holographic case, there are examples where the KMS condition admits an infinite number of solutions, and by truncating in this way, even if you do a soft truncation, you're basically losing sight of all the solutions that exist. And that for us was a big issue. So in generic problems, one needs to tackle the full set of CFT data. One has to go beyond the linear regression problem to a non-convex optimization problem, which is what we're doing with the unknown functions. and the neural networks. And in that sense, hard or soft truncations are inadequate. That doesn't mean they are inadequate in all the problems. Like, for example, in your application of in the Owen vector model, you got very nice results. And that is a signal that there, probably the spectrum is enough to get a fixed solution, which you can get nicely with your methods. So let's apply now. Let's apply this in several examples, and I will finish in 15 minutes to see exactly how this works and where it becomes difficult. Okay, so let me start with generalized free fields as a testing ground. This is a simple case where everything is analytically known. For a scalar GFF with scaling dimension delta phi, the two-point function is expressed as a sum of over images. We know it explicitly. We can do the OP expansion, and the thermal OP coefficients A and 12 here, can be deduced from the exact solution exactly. The operators that appear in the thermal OP expansion are the double twist operators labeled by n and the spin j, and their scaling dimension is twice delta phi plus 2n plus 12. Now, if I go back to my equation, so I will write an equation like this now, and now if I want to approximate the discontinuity using the thermal OP in the cross channel, in the T channel, then all these double twist operators will not contribute. They have vanishing discontinuity. And in that case, this is a very simple case. So the GFF is a very simple case because in the discontinuity, only the identity contributes. And this is how the identity looks like when I approximate it by, you see, I'm also cutting off these integrals. I'm not allowing them to go outside the common region of convergence for the SNT channel OPs. This doesn't make a big difference because in any case, KJ star is suppressing contributions away from the branch points. The approximate KMS condition with only the identity exposed and everything else put inside the tails looks like this. We have the discontinuity part here, crossed, appropriately crossed. R tilde, the tildes refer to the cross channel. Okay, this is the identity contribution, and everything else is put into the tails, and J star is arbitrarily chosen. So let's do some examples to see how things behave. Let's do d equals 4 and a random non-integer scaling dimension 1.68. And so I have all sorts of choices here on how, I pick the selection rules from this crossing equation. I can take derivatives at the crossing symmetric point, which is the usual practice here. Because I have functions and I'm modeling functions in space, it's more natural to evaluate this equation at different points on the Z grid, on the RW grid. And here I chose a grid which more or less captures all of the region of the common convergence region of the SNT channel OPs. Notice that there is non-zero spatial separation here, which is, I think, a novelty. In fact, in the grid we chose, we try to avoid the zero spatial separation region, which is the real axis, W equals 1. And then so all the blue points are the points that are taken into account when we try to minimize the corresponding loss, when we try to train. And the orange points are points where we get some configuration, then we test, we evaluate it there to see how well we're doing. So this grid point has 243 points inside this region. So this vector, crossing vector that I was mentioning before is 243 dimensional. Let's do a first test. How good is the approximate KMS condition? Because I did an approximation in the discontinuity part. So let's substitute the exact analytic GFF solution to the equation and check the loss as a function of J star. Now you can see if I do this absolute loss, then you see as I increase J star, indeed it goes down. Okay, if I do the dot loss, here you can see, more explicitly how quickly the angle goes to 0. Very quickly it goes to the order of 10 to the minus 10. So J star equals 8, for example, looks like a very good approximation. Let's expose now one operator. I cannot expose the phi squared operator because it does not contribute to the KMS condition, but I could expose the next one, say the one that has n equals 1, so one box phi. It turns out that this, although I'm at non-zero spatial separation, this comes together with the spin 2 operator phi 02. And this happens because of some peculiar identity that we noticed, where when you do the crossing, these two contributions basically become degenerate. So in this particular case, and only in this particular case, although we're not working at zero spatial separation, the only coefficient, from these two that we can determine is this combination, which is exactly the same one, the spin averaged that you have for this spin, not the spin, for this particular dimension in the zero spatial separation case. Okay, so let's expose this particular combination. Then we pull it out of the tails and write it separately, and the tails contain all the rest, plus the discontinuity part, plus the identity part. And this is now the crossing equation we're trying to solve. Now, at this point, I'm not trying to solve it. I'm just substituting inside the exact analytic values of these functions just to see how well I'm doing with this particular equation. I'm just trying to test how good the equation is. And you see here, I'm using that dot loss again, J star for 2, 4, 6. You see the dot loss gradually goes to 0, to order 10 to the minus 9. And here you can see explicitly how the resulting A, how do I get the resulting A? I get it from, I get it from this formula here, okay? So by using the analytic solution, I'm determining this part of the crossing equation, the F's, the H's, everything is known, and I'm using this equation to determine the unknown exposed one-point function. And you can see that the values that I get very quickly converge to the analytic one, which is 15.06. So this is all clear signal that these equations are okay, and you can systematically control the error. Now let's do the actual exercise where we now I'm not going to use any information from the analytic solution. I write down the equation, no exposed operators, and I'm just doing optimization with the neural networks to try to find the right tail functions, right? So no exposed operators means, do you have the equation? I'm working with this equation here. And I'm trying to determine the only unknown functions, the only unknown data are these functions. So I optimize, and this is the type of result I'm getting. You can see the result is capturing the tails. Here I use J star equals 6. So A4 and A6 are pretty well captured. It seems to have difficulty capturing A0 and A2. So the tails for spin 0 and 2. Although if you sum their contribution in the crossing equation, it seems to be capturing that quite well. You can see the losses are down. Nevertheless, it's not recovering fully the exact analytic solution. And that's the first signal that we're missing something here. Okay, there's a difficulty, we're missing something here. And playing a bit around with it, it's clear where the missing part is. Notice that in the crossing, so when I chose the 253 points, the region where I evaluate my crossing equation, I left some points in the rims of that region, the convergence region. Basically Z's, absolute Z's from 0.95 to 1, although this is a very tiny region in the rims of that. And I didn't include it because basically I have divergences there and it's hard numerically to take them into account. But it turns out that this region has an imprint, is basically making the optimization miss the actual solution. You recover lots of solutions that are not, that are basically false minima. If we repeat the same exercise with one exposed operator, again, this particular combination, you see we get similar results. And here you can also compare the numbers. You see in this way we get 13.29 plus or minus 2.82 versus 15.06. Okay, so it's ballpark correct, but because of this difficulty here, it's not really recovering all the tails. So, and this is the difficulty you have to deal with. There is an approximate reconstruction of the analytic correlator. This is the good news, which supports the claims that tails can be bootstrapped, but the result is not very accurate. And the sensitivity lies in the region close to R equals 1, and without it, the optimization is not stable. So basically, here I'm also putting a term which can be analytically determined, or that determines how these tails go close to, how they behave, how they diverge close to 1. And it's, you know, you have to really go exponentially close to 1 to capture this accurately. Even if you put it at 0.9999, you're not very accurate. And even if that thing is there to guide how the asymptotics of the tail go, you still are not recovering the right result. So the message here is that the missing information from the region near the boundaries of the ST convergence region is important. So can we overcome these deficiencies with additional selection rules? Then we noticed that if we fix the value of the function at some point, so somebody tells you that, okay, there's an extra information, which is basically extra sum rules, telling you that these tail functions have a specific value, say at some point, that I call here R intermediate. Here I took it to be 0.7. Its precise value doesn't play a lot of, doesn't make a lot of difference. But if somebody tells you where the value of these functions is there, then you get excellent results. And that in itself is already a bit surprising because, you know, you just gave me 4 extra sum rules. And then all of a sudden, you know, I get stability, I get a solution that is very close to the analytic one. And the same happens if when I expose one operator, you see here, I get the result 15.0647 compared to 15.06. So this extra information is very useful. Now, what happens if I supplied that information, but it was the wrong one? So it was not the information that you get from the exact analytic solution, because in principle, if I want to solve that problem, supposedly I don't know what these values are. I haven't solved the problem, so I don't know what these values at R intermediate are. And we noticed another interesting thing. We noticed that when you supply false information, then stability is lost. And we only recover stability or an island of stability when these values have a specific value, which is close to the exact analytic one. And that raises the exciting possibility that we can recover the exact solution, or if you want, we can mitigate for the problem of the missing information on the rims of the training region, of the convergence region, by identifying an island of stability in the space of the fixed vector AJ, evaluated at, say, 0.7 here. Okay, so can I take 3 minutes to tell you what happens in the holographic correlators, and then I will stop because I don't want to go a lot over time. Okay. Okay, so so this is the situation in the GFF case. It's useful because it's telling us what works and what doesn't work and what we have to pay attention to. And then we thought of applying this to another more interesting example where we don't know the solution, where many people are interested in getting the solution, the case of holographic theories. So large C holographic CFTs with a supergravity dual. This case is interesting for another reason. It's because once you give me the spectrum, and the spectrum here comprises of the double twist operators, the energy momentum tensor, and multi-traces of the energy momentum tensor, the spectrum is fixed, but the solutions we know from holography is an infinite family of solutions. Basically, they correspond to arbitrary higher derivative gravity theories, and they correspond to different solutions of the KMS condition. So this is an interesting example where if we did a convex optimization, we would identify just one solution, and then we'll miss the whole thing. So in holography, the 2-point function can be computed by solving the wave equation on the black-brane background. And the OP expansion of that result will give you, in principle, all these unknown coefficients. The energy momentum data are easily determined from the asymptotics at infinity, turns out. So you don't need to have the whole solution. Just from the asymptotics, you can get the AT and AJK coefficients, the non-double twist data. And the double twist data require the solution everywhere in the black brane geometry, and that has proven to be difficult to implement. There are also some other relations here, like universality relations that Fitzpatrick and Huang noticed. They noticed, for example, that the lowest twist energy momentum multi-trace data are all determined by AT, the one-point function of the energy momentum tensor. So what can one ask from a bootstrap computation? Well, you can ask that it detects the multiple solutions, that detects the universality relations, and also, for example, you can supply complete or partial energy momentum information from the energy momentum sector, and ask to recover the double twist data. And in a very nice exercise, Buric, Gusev, and Parnachev did precisely that using the zero spatial separation approach and Borel-Pade approximations. So let me quickly show you a few slides of basically what happens when we apply our approach here. So let's choose J star equals 6. Let's fix delta phi to 1.5 so that we can compare with Andrei's results. And then we approximate the discontinuity with a very humble set of only seven data that are supplied from the holographic calculation in the Einstein gravity case. So we're supplying data that will go into the discontinuity. The double twist data do not contribute to the discontinuity again. So the identity, energy momentum, T squared, et cetera, et cetera. And the values of the corresponding one-point function coefficients have been computed from holography. We expose again this combination of A10, A02, and then we look for an island of stability. And we do that dynamically in the following way. So in our four-dimensional space, we have four unknown tail functions evaluated here at 0.5. Remember, we try to fix, essentially, find the point where we supply fixed datum here, the value of the functions, the tail functions, and it has to be such that the optimization is stable. So the way we do it is basically we start from the GFF value. We know that that's not the right value, okay? And then we run the optimization, allowing it to basically play around with this value freely. So inside some sphere, it can play around and just move it around and see what happens. And then initially, if the sphere is very small, you do not achieve a lot of the losses that you achieve are not very low. You have lots of variation in, so not a lot of stability. But as you start increasing this yellow region, at some point it encounters the true value you should insert. And there, you expect to see that once you first cross, you should see enhanced stability. And then as you increase it further and further, basically you lose stability again. It's not clear this will happen. I will skip this, but this is precisely what we observed. We observed that when the yellow ball was very small and the values that we were fixing on the tails were the wrong ones, we were getting a lot of variation in the results of the optimization. How do we trace the variation here? Basically, we run the same algorithm, the optimization. We run the optimization 1,000 times on a cluster, and we see if what the standard deviation in the final result is. Then we notice that as we increase the radius, there is a point indeed where the standard deviations become very small. The tails, the produced tails are very well defined. They do not vary a lot. And then you still continue increasing that radius of the sphere. Then again, it goes bogus, just like standard deviations become large, the curves get deformed, you get really bad results. So we pick that point, that radius where the result has stabilized, and from that particular optimization, we read off the corresponding one-point coefficients. And this is what we get in this particular case. We get something around 9.37. And if you compare it with Andrei's much more reliable method, it's ballpark correct. It's still not as accurate as we would like. So there's a discrepancy between 9.37 versus 7.68. So these are the typical numbers that you get here. Notice that when we compare these two methods, we only used 7 energy momentum data. They used 40 and higher to start seeing convergence. If you do an independent numerical calculation of the PDE, again, it's not easy to find the solution, and you find it within some interval that is between, again, roughly 9 and 11. Okay, so our result is not worse than what you would, at least the first go, you will get from a numerical solution of the PDE. I'm quoting here the result that was reported by Andrei and collaborators in this paper in May. Okay, so I want to read everything. The take-home message here is that high-energy OPE tails can be bootstrapped. Various elements need to be combined in this type of bootstrap, but I hope I have convinced you that this opens the road to many new explorations. And there are many more applications to try at 0 temperature, finite temperature, holographic, non-holographic, with or without defects, all sorts of different things one can try. So I'll stop here and thank you very much, and sorry for going a little bit overboard.
Let me ask you, so first I